right. So I guess if we are streaming, and hopefully we have somebody streaming all the way from Italy. You cannot possibly adjust, for the time difference in the day. So he's probably going like.
It takes like an hour. Maybe
It depends on what you do on the airplane. If you stay awake the whole time on the airplane, you'll be fine. You'll adjust quickly. But if he's going for all the free movies on the airplane, oh, it's gonna be hard. Yep. All right, so let's go ahead and take a look at the answers. I actually got all the answers already put into the question, one of the versions of a copy of the question sheet already. So let's go over these. This is question number 1. For many operations, it's important, la 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 la. But the whole point is, using the current architecture, why can't we do this already? Okay, that's what it's asking. Okay, so let's look at the important part. Okay, so the important parts are here. Do not change the flags register. I do not want the side effect of changing the flags register, and I do not want to access memory for the constant that we are adding. So I don't want to use the add I or the sub I instructions that we talked about in the practice test. Is that okay? So now that we understand that these two are the key criteria for the new instructions, then we want to answer the questions. Why can't we do it now? Okay, so explain why such opcodes cannot be implemented using the current architecture. And the answer is whenever the ALU is enabled, the flags registers are also automatically enabled, because the enable to the ALU and the enable to the flags register are exactly the same thing. So there's no way to use the ALU to do any calculations without potentially overriding the flags register. Okay, so that's reason number 1. Reason number 2 is we do not want to use memory to supply the second operand, and yet right now the second operand only connects to a register in the register bank, and the only way to get something into a register is the LDI instruction, which is using memory access, and there's no pathway. Okay, let me just bring up the current architecture so you can see it a little bit more clearly. So what I'm looking for in this case is an explanation, of why it is not working at this point. Okay. So the first, there are 2 parts to this question. The first part has to do with the flags register. The EN of the flags register is connected to the EN or the enable of the ALU. So there's no way you can use the ALU without changing the flags register. So that's the first part, of the answer. And then the second part is there's no pathway. Into has no pathway to connect to a constant. Okay, it connects to the multiplexer of a register. Okay, but the register still needs to be initialized with a 1, right? So where are you going to get that 1? You still have to get it from memory. There's no constant. Okay, how many people went back and changed their answer to question number 1 after you saw the picture on question number 3? So it's there. Okay, so the answer of question 1 is actually kind of sort of built into question number 3. So by the time you go to question number 3, if you get question number 1 like not exactly the right answer, you look at that picture and go like, oh, okay. Go back, change a few things, right? So it was actually by design. Okay, I actually designed the questions that way, so that this one is only 2 points. Even if you miss it, it's not gonna mess up the whole test. Okay. So question number 2, the toy processor has some opcodes. So this one is kind of independent to question number 1. It's basically just asking where can we steal 8 opcodes. Okay, which useless opcodes can we kind of recycle and use it? And I kind of gave you the answers within the questions, within the question itself. Okay, so let's go ahead and read this part here. The toy processor has some opcodes that are not particularly useful. For example, and AA updates the flags register, which is useful, okay, because this is how you can test a register and say, okay, is this register a 0? Okay, because after a AND AA, if the Z flag is set, then you know the register is a 0. It's the same thing as comparing to 0, except you don't have to use 0 for comparing. Okay, so AND AA, AND BB, AND CC, and DD, those are actually useful, okay? But if you use AND AA for that purpose, OR AA is useless now. Because A and A is the same thing as B or B, which is the same, A or B, A or A, and A or A as an expression is the same thing as A and A as an expression. So you only need one of those two. Okay? So you can basically say you can hijack, okay, or AA or BB or CC or DD for increment. Yep. And then between these two, compare and subtract. One is more useful because subtract AA is actually useful in some cases, because if you want to clear the value of a register, sub AA can do that. Because you're subtracting A from A and then storing the result back into A, right? Well, that's guaranteed to be a 0. And very often we want to reset a counter back to 0, so that can do the job, which means it is actually useful. What about compare AA? What do you think it's going to do? It's almost the same thing as subtract AA, with one minor difference. What is the minor difference? It doesn't store the result. So A remains the same thing as it is, except you know that the Z flag is going to be set, because A minus A is always going to be a 0, right? The carry flag is always going to be cleared, because you're subtracting a value from itself. You cannot trigger a carry. The sign is going to be a 0. Overflow is going to be a 0, which also means the L flag is also going to be a 0. So you know that result already. Why would you want to do that if you already know that's how you're going to change the flags register? Doesn't make sense, right? So those are the two families of instructions that you can borrow. So the answer is, so assuming you're using AND XXXX, to test to test a register, so that means we can hijack or reuse all the OR XXXX, which means it is the same register in this and also in this place. Is that okay? Is everybody okay with that notation? Is that okay? And also because compare XXXX is also useless, we're going to recycle those as well. Now there may be some other instructions that you can recycle, but these two are pretty clearly useless and can be recycled. In other words, the answer to the question is in the question itself. Is that okay? I mean, did you guys get that part?
I misunderstood the question.
You misunderstood the question?
Yeah.
What did you write down?
I put and I just named like 8 different opcodes.
Right. Yeah,
Like how to get increment or decrement.
Yeah.
That's what I thought you were asking.
I thought it was which ones can you look at to kind of mash together to make it
Increment or decrement.
And then put it to.
That's all I was like, what the heck?
Yeah.
You guys didn't get this part? Oh. Somebody cranked it all the way up.
That's correct.
Are you awake now? Are you deaf now?
That too.
No, you're supposed to say, what? Okay, well, I'll take a look at your answers and see if, it makes sense or not, okay? Okay, question number 3 is really kind of the meat of one of these questions. The current toy processor architecture lacks support to supply a constant value to the ALU that is not from RAM, okay, which is what we're trying to avoid. We don't want memory cycles unless we have to. Part of the change is already proposed as follows, okay? So it's already done here. I'm adding this new mux here. This was not there before. To get this done, I actually have to move certain things around to make room for the mux. There's also so this unknown tunnel is connected to the select pin of this mux, and then it's connected to this NOT gate, and then this NOT gate is connected to the enable of flags. Okay? So this is the proposed change. But your job is to specify what goes here, enhance the question mark, okay? Whatever you do, I want to make sure that there's no need to add any bits to the width of the ROM. So we're not adding any tunnels, we're not adding any signals coming out of the ROM or the data port of the ROM. I want to maintain the operations of all existing opcodes without any microcode changes, okay? In other words, all the existing opcodes, the microcode of all the existing opcodes should not need to be changed in order to accommodate, this little architectural change here. And then the last one is I also want this change to give me a mechanism in order to implement the increment decrement register opcodes. That is question number 4. The exact detail of how to do that is in question number 4. But whatever you do here in step 3 has to support step 4. Okay? All right. And this is kind of my guideline to your answer. So your answer needs to express the expression, which is going to be a logical Boolean expression that connects to the select input pin of the new mux, and that would be the question mark here. So you have to give me an expression, some kind of Boolean expression, so that you can use the output of the Boolean expression, which is going to be in a hierarchy of gates, in order to specify what goes into the select input of this mux, and also what's going to be negated before it goes into the enable of the flags register. And then number 2 is going to be the more important part, which is explain why this expression works to maintain the microcode of existing opcodes. In other words, you have to know the existing microcode of the existing opcodes first, because otherwise you cannot argue and say that, oh, this won't have any impact on the existing microcode. And the proposed answer, or at least one of the answer, is this. It's the negation of the conjunction of ALU enable and register output 1 demux. That's only one of the possible output, one of the possible answers. There may be some other answers too, okay? But this is one of them, okay?
What are others?
Sorry?
What are other answers?
I don't know yet.
Oh, so.
This is one of them.
Oh, okay.
These two are the same. This is one way to express it. This is the alternative way to express it after you apply De Morgan's law. So the negation applied to the conjunction of ALU enable and register output 1 demux is the same thing as negating each item, but then you use a OR to connect the two. But they're equivalent because of De Morgan's law. Okay? So the explanation of why this is going to be okay is because register output 1 demux is a 0 only when we need to drive the address bus, and that's when we have the load or the store instructions. For all the arithmetic instructions, you will recognize that register output 1 demux is a 1, and so is ALU enable. Those two are going to be 1s for all the current arithmetic opcodes. Is that okay? So if we know this, and then we go back to this modification here, and we say this pin is really the negation of the conjunction between ALU enable and also register output 1 demux, then you can see that it is always going to be selecting which one of the mux. With existing arithmetic instructions, which input of the mux is it always going to be selecting? 0, which is connected to the output 1 of the demux, which used to be hardwired into of the ALU. So it doesn't have any impact as far as into of the ALU is concerned when we are talking about arithmetic instructions. Okay, that's cool. What about the flags register? The flags register with current instructions is supposed to be updated every single time the ALU is enabled, right? But every time the ALU is enabled, register output 1 demux is also guaranteed to be a 1. So if this thing is a 0, this is guaranteed to be a 1. So every time we select input 1 of this mux, the enable pin of the flags register is also guaranteed to be a 1, which works out because that's the way that we had in the old architecture. So it's not going to have any negative impact on existing instructions because of that. Is that okay? So that's the kind of explanation that I'm expecting. Yep.
But it's negated.
Yeah, it has to be negated because this pin goes to the select pin here, and we want input 0 to go to into normally, quote unquote normally, but at the same time, when we select input 0 to connect to into, we also want the flex register to be enabled.
So,
Yep.
why does the ALU enable have to be part of that input?
Why is
Because I just had the
negate the
RO1 demux
negated?
negated. Is there any reason why it has to be and the ALU enabled?
I see, that will work too. Because ALU enable and our register output 1 demux are always enabled at the same time with the current instructions. Yeah, that will. I'm just looking for a possibility of enabling the flex register when it's not supposed to. In other words, if you hook up this wire directly to here, right? That's basically what you're saying. So that means every single time this is a 0, that's going to be a 1. So if this one is a 0,
If that one's a 0, then
Yeah,
it
then
won't
it won't go to the mux, the input 2,
it won't go to the mugs,
because we need a 1 for that
but
one.
we still don't want the flex register to change.
Right, but the new mux won't get, it's not gonna get the information from the register bank. Because it's
It's gonna be negated.
it'll be a 0, right?
But you might still have a, but the ALU can still be spewing up something at that time. So what we need to do now is to figure out, okay, with our RO1 demux being a 0, what is the ALU possibly doing? So let's go to Logisim and go into the ALU, zoom out, and track down the enable line here. So the enable is it's controlling the mux that output overflow, carry, but then the other ones, then it won't be specified if it's turned off. Okay, so we have a situation here, because if ALU EN is off, okay, because you're doing an LD or ST instruction, right? Then the ALU is quote unquote off. When the ALU is quote unquote off, these two muxes are also off. When the mux is off, the output is undetermined. It's like, it's just floating. It can go in either direction. It's not driven. But those are going into the flex register as the output. Okay? So when you enable the flex register will take whatever signal is fluctuating on that wire because it's not getting driven and update itself.
No way we would know that.
Sorry?
We just know that though.
We wouldn't know that?
Before you told us that.
Oh. Well, it is in the ALU design itself, so you get partial credit because you still need to gate it with ALU EN, because that's the surefire way to make sure that every time you turn it on, ALU is enabled, and on top of that, you also have register output 1 demux being a 1. So I cannot give you full credit, but I can give you partial credit.
What if we just use that logic that every time ALU is enabled, the other thing is also enabled, so we just connect it straight to ALU? Will it work?
But then you miss the other part of the question, because the other part of the question is
What will be
it has to support the increment decrement register opcodes.
So it will not support this.
It will not support that because this requires you to disengage the flags register while you increment or decrement. So if you maintain that tie between the ALU enable and also the flags enable, that means every time you increment, it will also change the flags register, which is what I don't want. Yep.
Wouldn't the flags register be disabled though?
Say that one more time.
Wouldn't it be a disabled flags register? If you use the negated R01 demux,
Mm-hmm.
wouldn't the output would be so we use it whenever it's a 1. It needs to be a 0 to enable the mux.
Mm-hmm.
And then later it will turn into a 0, so the flags would be disabled, right?
Okay, so this is what I want to use. This is actually easy to understand. So this is what I want to use to specify the question mark.
Yeah. So, but if you only specify the question mark with R01 demux,
Mm-hmm.
but negate the output,
Yeah.
wouldn't that work? Because it will it will make it, whenever we want to use it, it'll be a 0, but then later it'll be negated to a 1 before entering the
Right. Okay, so when R01 demux is a 1, we want to use, it's also a signification that we want to use the ALU.
Yeah.
When it's a 0, that's when we want to utilize register output 1 for something else, right? So if you hook up R01 demux directly to the question mark here, it's definitely not going to work because of the negation. If you negate it first, then it will serve the same thing as ALU enable, because at this point all the instructions would have ALU enable and R01 demux enable at the same time.
Okay.
So they are currently tied together, and that's what I'm exploiting to implement the new instruction, because I would just say that sometimes we'll enable the ALU, but register output 1 demux is going to be a 0 instead of a 1, and that will signify the processor and say, hey, use the constants, not the output from the register bank. Okay. So I will have to look at each in each answer that you guys turn in and see whether it will work or not. It will meet all the requirements or not. I'm guessing that most of your answers will at least address some of the criteria, but may possibly not all of them. So I'm gonna have to kind of check each one. This is going to be fun to grade.
As always.
As always. Well, if it's not multiple choice, it's always fun to grade, right?
Yeah.
Multiple choice is like, oh, come on.
Just Scantron at the end.
Was the last test curved, or was that the pre-curve?
It is not curved yet,
Okay.
and yet the distribution of the grades is actually pretty normal. It's not it's not bad at all. Okay, so with this one, this is the answer. So as far as I explained why the flags register is not impacted with all the current instructions, and this change supports the new instructions because it allows ALU EN to be 1, and yet the EN flag, EN or the enable of the flags register to be 0 by making R01 demux to be 0, which also at the same time will select a constant of 1 to connect to into of the ALU. So that's my argument to say that this will work to support the new instructions. Is that okay or not? Sort of?
It makes sense now.
Makes sense? Now, okay. All right, so so for question number 4, this is the last step of the whole thing. It's the actual implementation in terms of the microcode. Okay, so for my particular answer, I'm assuming that I will basically reuse OR XXXX for decrement XX. Okay, so when you look at the opcode of OR XXXX, it will look like this particular bit pattern. Okay, 1101. Originally it is XXYY, but because it is the same, YY is the same thing as XX, so it becomes XXXX. Okay, And then these 4 zeros need to be padded here, because when we decode an opcode before it becomes an address of the microcode pointer, it will pad 4 zeros to the least significant side.
So, do you have to do it in hexadecimal then?
You can do it in binary like this, or you can do it in hexadecimal. If you do it in hexadecimal, I would do it like this. It would be 0x, that's a D, okay, 0, 0, or, and then you just have, XX, shifted 6 times, and then or, XX, shifted 4 times.
Let's keep it binary. Let's keep it in binary.
What?
Let's keep it in binary.
That's not binary. Let's
forget about that. That's hexadecimal thing.
So you can use either one.
But how come decrement is closest to or instead of being closest to sub, which is.
You can use subtract if you want to. If you use subtract, it just looks different. So if you use a subtract, when you look up the opcode table, if you hijack compare, so compare is where's compare? Right there. So if you use compare, it's going to be E instead of D. But the rest will look exactly the same. So if you use compare, then this is going to be an E instead of a D. But the rest would still be the same. Okay. So then we have to specify each field of your microcode slice and do the selection. Microcode pointer select should always be a 1 because we are just going to be incrementing to the next slice. PC enable should be a 0 because we don't want to update the program counter in this case. So that one needs to be a 0. If program counter enable is a 0, it doesn't matter what you use for PC mux because we are not changing the program counter. PC mux is only used to specify, oh, you want to change the program counter. How do you want to change it? Well, since we're not changing it, you can do anything you want with PC mux. So that's why this is a question mark. Address mux is also going to be a question mark because RAM is off. Okay, RAM select has to be a 0 because we don't want to exercise RAM, so that has to be a 0. So if RAM cell is a 0, then you can specify anything for address mux because the address line can be connected from anywhere. We are not using it at all. RAM load can potentially be anything because we are not using it. We are not using RAM at all. ALU OP has to be 0, 0, 1. Okay, or you can just say 1 if you want to. Just use base 10 because we are specifying the subtraction operation. Okay, ALU enable has to be 1 because we are enabling the ALU. Register output 1 demux has to be a 0 because that's the whole point, right? Of the previous equation. Register output 1 select can be anything because we are not really using that particular output. Okay, so it can be anything. So you put a question mark here. If you want to emphasize this is like up to 2 bits, you can specify 2 question marks, but 1 would be fine. Okay. Register output 1 demux has to be a 0, 1 because in the circuit diagram, we still want register output 0 of the register bank to connect to in 1 of the ALU. So that's why the select pin going into this demux here still needs to be a 0, 1 in order for that to work. Is that okay so far? Okay. Yeah, go ahead.
So why are you not using the program counter in this case?
The program counter has done its job already. We have in fact decoded the opcode already at this point, so we don't use the program counter. The program counter is pre-incremented already before we got to this instruction. Location 001 in the ROM is incrementing the program counter already, so we don't have to do a single thing to do with the program counter. Okay, so next one is register output 0 selection. That has to be XX because this is the register that we use for incrementing, so it has to be the output from the register bank. And the same reason why XX is also specified as RI cell because we are updating the same register after the operation. So these two XX must be specified there. RO0EN has to be a 1 because we have to enable register output 0, so that has to be a 1. RIEN has to be a 1 because we have to enable the register input to update that particular register. RI mux has to be a 1 because there are two paths to specify, how we update the registers. So we have to select the correct one. In other words, when you look at the input here, it's coming in through a mux. So we have to specify the correct, path by specifying a 1 in RI mux. So that one has to be a 1. That's it. The only one left is IREN has to be a 0 because we are not doing anything. We are not updating. We are not decoding. So we don't want to mess around with the instruction register itself. Yep.
Can we at some point go back to question 2 because I totally don't understand.
Question number 2?
Yeah. No, you knew what I mean.
So question number 2.
So
Mm-hmm.
you weren't asking us to try to use those to create a
I'm asking what can you use
You're using
to...
it to hijack those codes. See, I totally didn't understand.
Yeah, that just
So I would just like draw on a line. How can I possibly increment or decrement using those operations?
That's what I
Plus,
thought.
that 4 has 5 slices. Like I'm going to use different operations.
That's what I thought
somehow.
No,
I mean, why did you put
Okay.
5 slices there?
Well, just so that, if you need to use 5, go ahead.
So that made it very confusing.
Okay, yep.
Yeah, I replaced number 2 was with each register, so I use like 4 slices. So instead of XS, I put like 0, and then the X size I put.
It is supposed to be parameterized like this. But if it is just, if you're just changing the register to illustrate how to do it with each register, I can understand that part. So, as long as it is consistent, like, you're using 0, 0, and then you use 0, 0 here, and then 1, 1, 1, 1, I will still count it as okay. Yeah.
So what is slice 1? It's just all zeros? Slice 1?
Slice 1, we don't even use slice 1 because slice 1 needs to actuate something that is not in the table, which is the reset line. Yeah, so it has to actuate this particular line here, which has no name. So, so we don't even need to specify slice 1.
It's the microcode reset.
It's the reset, but there's no label here. But in the code, in the C code, there is the label. Yep. Okay, very good. Yep.
Luckily for question 4, there's no explanation to be done yet. So
There's no explanation, but there's all these things that need to be. Some needs to be 1, some needs to be zeros, and some need to be question marks. Yep.
So if it's not question mark, but it's like, something else, like, for example, the PC mux, I put down, like, I don't know why
That would be marked as incorrect because because it is specified in the question for bits that do not matter. Use question marks to designate don't care. Your score is affected if a don't care bit marked as 0 or 1 or vice versa is marked. Okay, bad grammar here.
-1.
extra credit.
But that's why that's why the question mark is important because I specifically say use the question mark when it's a don't care.
yeah, with RAM it makes perfect sense when you say since it's off, it's 0, then load, we don't care about the load.
Yeah.
It can be anything. So
Yep.
this makes perfect sense.
But the same thing goes for PC mux mux because PC mux mux is utilized here, and then you look at PC mux and PC inc. Those are only used when you are selecting the path to update the PC, right? In other words, PC inc is utilized here, which impacts this line, and then PC mux is used here, which impacts which path you're selecting. But those do not matter at all if your PCEN is a 0 because you're not updating the program counter. So you can use any PC mux mux and any PC PC inc. It doesn't really matter.
So if it doesn't matter, then whatever value we put in the answer will be correct. Right? Yeah.
Not if I say specifically to use a question mark. Yes.
That's what question marks are everything.
Well, in actual computer engineering, you will find why the question mark is actually important, because sometimes when something is a don't care, you can actually use it for something else. Okay, so it is important to know that which one can be either a 0 or 1. It doesn't have any impact. Alrighty. So the last one I think is probably the easiest one. I cannot imagine anything that is easier, because this is almost the same thing as the practice test. Okay, except it's even more spelled out. I mean, I gave you all the space and spelled out the whole thing.
The instructions are clear.
Yeah, very
Instruction is very clear. In fact, this is short of writing the actual C code and ask you guys to trace the C code line by line. Okay, so this one, I don't think I need to explain it too much, but I can just quickly go over that. Step 1, I don't think anyone can miss step 1, because it's just copying the Mantissa to here and copying the exponent of 10 over here. Cannot go wrong. I did not even provide a place for the sign, so if you don't specify the sign, it's okay.
Well, I specified it, but it wasn't.
We'll
I
get it
included it
later.
Right, it's not in the format. Step 2, okay, so step 2 is a little bit more involved, because I want to change the base 10 Mantissa and the exponent so that the Mantissa becomes an unsigned integer. So you have to shift the binary point all the way to here. But every time you shift it from one place to another place, you are changing the value by 10x, right? So you have to compensate for that by decrementing the exponent by 1. So every time you shift the decimal point to the right hand side by 1, you have to decrement the exponent by 1 to account for that. Okay, so we have to move the decimal point 5 times, so we have to adjust the exponent of 10 5 times as well. So 1 minus 5 is -4. Okay, any questions about this part? No? Okay. So over here, this is the only tricky part is, okay, we want to get rid of the exponent of 10 by increasing it, right? Because it's a negative number, so we want to increase it. But how do you increase the exponent of 10 without affecting the actual value represented? Well, you can adjust the other two, okay? So the first step is to subtract the Mantissa by 10. Okay, but if you subtract this by 10, when you divide this by 10, dividing it by 10, it has a 0.5. We don't like a 0.5. Okay, so you can first multiply it by 2 first, and then you can divide it by 10. But when you multiply by 2, you have to compensate the multiplication by 2 by decrementing the exponent of 2 by 1, so that it is maintaining the same value. So that's how we got from 23125. Multiply that by 2, it becomes 46250, and then you divide it by 10, it becomes 4625. Okay, the next step, about the same thing. You multiply 4625 by 2, then you have to decrement the exponent of 2 by 1, then it becomes 9250, and then you divide 9250 by 10. You can now take care of one value, or increment the exponent of 10 by 1. And you do the same thing a few times, then you get the exponent of 10 down to 0. Your exponent of 2 would become -4, and then your Mantissa should be 37. So I think this part, most people got. I did not even use a calculator to do this, but some of you might use a calculator. Either way, you can just jot down some calculations on the side. Step 4 is to convert the Mantissa to a base 2 number. Your answer should be the base 2 representation of the Mantissa. So we are talking about 37, and how do we represent 37 as a base 2 number? You can use any way to do the conversion. I just pick out 32 being the largest power of 2, then we have 5 left. 101 is 5 in base 2. Done. Okay, so however you do this, okay, it's up to you. Okay, the exponent does not need any conversion at this point, so it's still in base 10. If you do the conversion right now, it's okay, but you will have to deal with it later on. So step 5 is to normalize the base 2 mantissa so that the value of the mantissa itself is between 1 and 2. So I want it to be in 1 point something something something. So that means we have to shift the binary point this time until we get to 1 point something. The binary point is implicitly here to begin with, so we have to move it 1, 2, 3, 4, 5 times. But every time we move it, every time we move the binary point to the left, we have to increase the exponent of 2 by 1. So that's why the exponent of 2 went from -4 to 1. Is that okay so far?
Damn, I messed that up. I totally forgot that you had to move the. No, I had it, but I just forgot the. Damn.
Well, partial credit. Okay, then step 6, okay, if you get this wrong, as long as it is consistent with what you need to do in step 6, I'll give you the points of step 6.
Okay.
Okay? So it's not like, you make one mistake and then
Over.
it's over.
Alright, it was over.
So each
Yeah,
step
yeah,
is
yeah.
checking consistency based on the earlier mistake. Okay, so if you make a mistake earlier, but that also means if somebody makes a mistake earlier and then later on magically fix that error in the later, that won't get credit either. In fact, that will flag me as maybe it's copied from another person, right? Yep.
Consistent error.
Yep. Consistent error is a good thing. Yes. Well, just ask, ISO 9001. That's a manufacturing process, certification. It is basically asking factories to document and do things consistently. So if what you do is not cranking out quality products, as long as it is documented and consistent, you will still get ISO 9001 certification.
Wow.
As long as your failure rate is always 20% consistently, it's okay. It's just we don't want it to be 5% 1 month, 15% the next month, and then back to 2% the next month. Okay, so we have step 6 here. Step 6 means it's saying that exponent of 2 is stored offset by 1023. You have to add 1023 to the actual value that you want to store in order to convert into binary. So in this case we have 1. So 1 plus 1023 is 1024. And we want it to be represented in base 2 in this case. So I just stated what the number should be in base 10, and then this is the base 2 representation, which is 1 followed by 10 zeros. Because 1024 is 2 to the power of 10. Okay? Step 7, now integrate the sign bit, the offset, exponent, and the fractional part of the mantissa in base 2. So this one is the sign bit. These are the exponent offset by 1023 already. And then this part is the fractional part of the mantissa, which is only this part here. And then I also say here, use ... to denote the rest. Okay, so since I have this 0 here, the ... means, just repeat this 0 as many times as necessary. Okay, because I don't want you guys to spend the time to count, do I have 64 bits? Yeah, so don't do that. So here in step 8, convert the base 2 representation into a hexadecimal representation. Your answer should have 16 digit. Okay, so I'm telling you explicitly, 16 digits, pad it until you have 16 digits. Okay, only the first 5 digits actually have something useful. Okay, so if you regroup everything into groups of 4, this is a C, this is a 0, 0, 2, 1, and then the rest are all zeros.
8. 0, 0, 2, 8.
Oh yeah, this is 2, 8. That's an 8 right there. Yep. Yep.
Is it okay to leave out the 0x when you write it down?
It is okay. Yep. So if you leave out the 0x, that's okay because it is already asked that you use a hexadecimal number, so it is implicitly hexadecimal.
Not use ...
Do not use the ... so spell out all the zeros. Okay. Yeah. And I even put a not in italic to emphasize.
That was pretty straightforward question. Plus, you provided us with, step-by-step pattern just to fill it up, fill the blanks,
Well, we also did it in the practice test. I
And
think that
practice
helps.
was pretty
Yeah.
close, yeah.
But the point is to make sure that you guys know, binary. Double precision floating point numbers, and we have proof that you know that. So that's good. So what do you think?
So,
The last one was perfect.
the exponent part,
Uh-huh.
that's 11 digits, 11 binary digits, right?
That's correct.
Shouldn't that be 0, 1, 0, 0, 0, 0, 0?
This one is coming from the sign bit.
Right. But then the next 11 are the exponent, right?
Yes.
Shouldn't that be a 0, 1, 0, 0, 0?
No, because there
Ten
are
digits.
We trimmed that.
because there are 11 bits to represent 1024.
Right. 10 of them are on the right, are the 2020.
But since you need, since you only have 11 bits, right? To
The most
represent.
significant bit isn't used, right?
Sorry.
The most significant bit isn't used.
The most significant bit is a 1.
But 1024 in binary uses 10 digits.
No, it uses 11 digits. It has 10 zeros after the 1. So it uses 11 digits
That's
altogether.
Alright.
I think, because it's 2 to the power of 10, which means it has 10 zeros after the 1.
Right.
Right, that's understood.
Well, that's a partial
Yeah,
credit thing,
that's
because you got most of the steps done.
I'll agree
you
with
know.
that.
Yeah. Yep. All right. Any other questions? Any questions about these answers? I might take out question number 2, because if the question itself is kind of misleading, might just kind of not count it in. Because I was trying my best to ask the question and not to supply the answer within the question itself, and that's
Which
partially.
you did. You did supply the answers.
Yes,
which
I did,
Which
yes.
we all missed. We're like, wait, where's the answer?
Well,
Yeah, like,
many people missed. Yes.
It's just the way it sounded was build a what was it?
I had no idea what I was doing.
But
I
how,
just
how
thought
would
you
you
meant
phrase
Totally
it?
missed the point, yeah.
Steal. Use the word, stealing.
I don't know.
I
Like, what
I
can
thought
you
like
use?
psycho,
No, I
you
just
look at the
listed out.
JOI, how does
Yeah.
it compare to J? Like that type of thing, where you look at them and you kind of see the similarities and try to morph them into one.
Like, how do you create an increment and
I
a
was
decrement?
like, oh, maybe you could steal the
with stuff.
Like we did in
like
the
the
whole
compare.
Yeah. Like stealing from
like we did
previous
in the-
opcodes.
Yeah, like.
Yeah, we're stealing the opcode itself, the binary pattern, but not what it does. Okay. So I might just knock out that one question altogether if I have to take a look at all the answers first, and make sure that it is like consistently the whole class can quite get it.
Yeah.
But the rest should be okay. I think the rest of the questions are fairly close to the practice test.
Yeah.
Except for that one.
Alrighty.
Way
The only
misunderstood.
guy is probably losing it right now.
Yeah.
He's like,
Well,
"Yeah, it's bad."
so what this means is on Thursday we're gonna start to use these 2 instructions.
Oh, Jack.
The increment and decrement instructions, they're very useful in stack operations. So we're gonna be starting to use these instructions.
Do we have to write our own opcodes for those, or are you gonna give us?
I would give that to you because our focus is no longer writing the microcode of the opcodes. Our focus is now starting to go into subroutines. Remember before the break we started to talk about subroutines. So our focus is to get to subroutines, and then we'll get to parameters hopefully, and also how to return values and stuff like that.
Recursion.
Oh, we'll do recursion. That's easy.
That's easy.
Yep. Alrighty. I'll see you guys on Thursday. Hang in there. 3 more weeks, right? Okay, we can stop the streaming. Bye, Scott.